Dear students, this is the ninth class that and it is the last class of on this chapter differential equation. And in this class, we will learn some other properties of dual operators and using them to solve some non-homogeneous second order differential equation. And that means this is the third part of solving of non-homogeneous differential second order differential equation. So come to those properties. Those properties are here. Those properties are here. Number one is this is the number 8 properties. There is fd e to the power ax and ux. So in this case, there is an exponential term and a function of x. So if it is in the form, then fd e to the power ax ux is equal to e to the power x is taken in the left side, and here d is replaced by d plus this a. So d plus a then ux. So from here it is clear that 1 by fd e to the power ax into ux is equal to this e to the power ax taken in the left hand side in the left, and then this d is replaced by d plus a. So f of d plus a then ux. And another important property is 1 by fd x dx. That means there is a term x and a function of dx. That can be written as that result x into 1 by fd into v minus f prime d by fd function of d whole square and v. So this is the relation. So we will mainly focus on these two properties, that is this one and this one. And this property actually we have already calculated. So mainly focus on this. We mainly focus on these two properties, and here are some examples of this kind of properties of FD, that is the operator. Here is an first example, that is d2y by dx square minus cx 6 dy by dx plus 9y is equal to x to the 4 e to the power 3x. So this is the form e to the power ax into ux. So I am not dealing much more with the complementary function. You know the process, the method, how to solve. But here finally come here the auxiliary equation has two solutions. M1 and M2 both are equal, and that is equal to 3. So the complementary function is a plus bx is equal to 3x. You know that a and b are arbitrary constants. Now the particular integral. The particular integral is equal to 1 by function of fd, then the right hand side, that is x to the 4 e to the 3x. So that is there d square minus 6t plus 9. Now you know that this has the form of this 1 by fd e to the ax dx, and you know that this is equal to e to the ax by fd plus a. That means in this case this d should be replaced by these 3. Okay, and then at the right side there will be only the term x to the 4. So e to the 3x is there, 1 by this d is replaced by d plus 3, then minus 3 whole square into x to the 4, or 1, and from there y2 is equal to 3x, then 1 by from here you can easily understand that there will be d square only into x to the 4. And you know that from here y2 is equal to the 3x, then d2 is equal to minus 2, because it is d square, so d2 is minus 2 x to the 4. And you know that this is equal to from here you can write this is equal to you know that d square, d means integration, d inverse means integration. So here d square d2 inverse means integration, there will be integration in there will be twice integration. So first integration of x to the 4 will provide you x to the 5 with 1 by 5. That is here, and d inverse, another inverse is here. So that will give you this e to the 3x is here, and x to the power 6 by 6. That means 1 by 6, 30 x to the 6. So this is the complete solution. Now solve this equation. This equation d2y by dx is equal to 5 dy by dx plus 6y is equal to x e to the power x. So here we should here is the steps to find out the roots of the auxiliary equation, that is m1 is equal to 3 and m2 is equal to 2. So the complementary function is this, and the particular integration is 1 by from here d square minus 5d plus 6x e to the x, that is equal to 1 by d minus 3. You can factorize it as d minus 3 d minus 2 x e to the x, and from here you can find you can obtain this e to the x is there 1 by d. This 3 is should be replaced by e to the a is in this case 1, that is 1. D plus 1, d should be replaced by d plus 1, that is here, and that is also here, into x, that is e to the x 1 by d minus 2 from here and d minus 1 is from here, that is equal to e to the x. You can write these two terms as 1 by 2 into 1 minus d by 2, and from here minus 1 into 1 minus d. Here is x. So from here 1 by from this 2 is, has this 2 appears here 1 by 2 e to the x, then 1 plus d by 2 this to the power minus 1 and into 1 minus d to the power minus 1 into x. So from here 1 by 2 e to the x, just I use the series of this. So 1 by half d plus other terms, because only d terms is non-zero, but higher terms rather than d will give you, when will be applied on x, will provide zero result, null result, and this commutator is 1 by d plus d square, that is x. So from here just simplify. So finally we get here should be x and here should be x, half e to the x, x plus 3 by 2. Okay, because this d square x d2x is equal to first derivative will give you 1 and then another derivative is 0, and all higher terms also. So finally you get y2 is equal to half e to the x, x plus 3 by 2. So the complete solution is y is equal to 1 plus y2, or y is equal to a to the 3x plus b to the 2x plus this half a to the x, x plus 3 by 2. Another one is here d2y by dx square minus 4y is equal to x sine hyperbolic x. So here is the complementary function y1 is equal to a e to the 2x plus b to the minus 2x, and the particular integral is here 1 by d square minus 4 x sine x, and that the sine hyperbolic x can be written in this fashion, that is e to the power x minus to the minus x by 2, and this term 1 by d square minus 4 into x is there, since sine hyperbolic x is equal to this. Now just separate this into two terms, that is y2 is equal to 1 by 2, this is 1 by 2, 1 by d square minus 4 x e to the power x, then minus half 1 by d square minus 4 x e to the minus x, that is equal to, you know that in this kind of uh, equation, in this kind of expression, this d should be replaced by d plus, since in this case a is 1, so d plus 1. So this is e to the x by 2, 1 by d plus 1 whole square minus 4 into x minus e to the power this e to the minus x by 2, then 1 by d minus 1 whole square minus 4 into x. So that is what e to the x by 2 from 1, and this just this can be written as d square plus 2d plus 1, then minus 4 into x is minus e to the minus x by 2, 1 by d square minus 2d plus 1 minus 4 into x. Just simplify this. So from here e to the x by 2, 1 by d square plus 2d minus 3 into x, and then minus e to the x by 2, 1 by d square minus 2d minus 3. And from here you can write e to the x by 2, and from here you can write this term as minus 3 1 minus 2d by 3 plus d square by 3 x minus here e to the x by 2 is there, and from here we can take it, this term can be written as minus 3 into 1 minus 2d of 3 minus d square by 3, this into x. So from here e to the x and this minus 6, 1 minus 2d by 3 plus d square by 3 to the power minus 1 into x, then plus e to the power minus x by 6, 1 minus 2d by 3 minus d square by 3 to the power minus 1 x. Just expand these terms and these terms. Expanding this term this and expanding these terms we get this. Okay. Now, 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 just you have to operate these terms on x. So first e to the power minus x by 6. This will give you x. This one and x. Then 2d by 3 is here. D means differentiation of x is equal to 1, 2 by 3. But other differentiation will give you, higher other differential will give you 0 result. And then e to the minus 6 by x, and from here x minus 2 by 3. Just these are the terms. And you can write these. So from here you can write that 1 by 6 into 2 into e to the power x minus e to the power minus x by 2 into x minus 1 by 9 e to the power x plus e to the minus x by 2, and you can write this in this way. So finally you obtain y2 is equal to this. So the complete solution is the complementary function and plus the particular integral. Now come to another one. This is another one, d2y by dx square plus 2 dy by dx plus 2y is equal to x to the minus x. So writing d in d operator form, this equation will give you this, and from here you have calculated two values of m, that is minus 1 plus I and into is minus 1 minus I. So the complementary function is e to the power minus x, a cos x plus b sin x. So the particular integral is calculated here. So 1 by d square plus 2d plus 2 x e to the minus x, that is equal to this x e to the power minus x is taken here. 1 is here and d is replaced by d minus 1. So that is here, and then x. So e to the power minus x, then here just simplify this x, just expand this term. So this, and finally e to the minus x d square plus 1 x. So e to the minus x 1 plus d square to the minus 1 into x. So e to the minus x, and you can expand this as 1 minus d square. Other terms, but other terms will give you 0 result on upon applying on x. So from here e to the minus x, and this will give you x, and d2 is equal to 0. d2x of d2x is equal to 0. So from here this is the particular integral. So the complete solution is this. Here is another example. d2 square plus 1y is equal to the power x into x to the 4. So here is the complementary function, that is here a cos x plus b sin x. You know how to calculate this. Here is written also here, and particular integral is y2 is equal to 1 by d square plus 1 e to the power x to the 4. It is equal to e to the power x, and you know that this x e to the power x should be taken here, and this d should be replaced by 1. So d plus 1 whole square plus 1. Just simplify. So d square plus 2d plus 1, and this one here x to the 4 that is equal to e to the power x 2 plus 2d, this 2 plus 2d plus d square into x to the 4. So write it as here e to the power x by 2 1 plus d square by 2 into x to the 4, that is equal to e to the x by 2 1 plus d square by 2 to the power minus 1, and then x to the 4, and just expand this, and after that simplify, you finally get the complementary particular integral as e to the power x by 2 x to the 4 minus 4x cube plus 6x square minus 12. So the complete solution is this complementary function plus this particular integral. Here is another example. And you go through this. Every steps are calculated here, and you will understand what has happened here. So we calculated here, so our complementary function as a plus bx is equal to x, because m1 and m2 are equal, and the particular integral as 1 by 12 x to the power e to the 2x. So the complete solution is this. Just go through that one. Another one is here d2 d2 plus 1 y e to the power x cos x. So this is the cos x case, and in that case complementary function just solve this. a cos x plus b sin x. Because in this case, m square plus 1 is equal to 0, that means m is equal to plus minus I. And pi is equal to particular integral is 1 by d square e to the power x cos x. That is equal to e to the power x taken here. 1 by d is replaced by d plus 1 whole square plus 1 cos x. E to the power x 1 by d square plus 2d plus 2, then cos x. And e to the power x 1 by, you know that this can be written as this d square should be replaced by uh, this is cos ax, a is in this case 1. So this d square should be replaced by minus a square, minus 1. That means minus 1. This is the formula. That 1 by f d square cos ax plus b is equal to 1 by f minus a square cos a plus b. So this is done here. After that calculation, you finally get that y2 is equal to e to the x cos x plus 2 sin x. So this is the complete solution. Here is another example. This example is similar to uh, that of somewhat like this one, equation 5, problem 5. That is, here you see here, look at here, that we have calculated the complementary function as this. m1 is 2 and m1 is equal to 1. So y is equal to complementary function is equal to a e to the 2x plus b e to the power x. And y is equal to 1 by d square minus 3d plus 2x cube. Okay. But in this case, there is no term including e to the power x or sin x, etc. Only x cube. So this first part is somewhat similar to of previous ones, but the particular integral will be different from those. So 1 by d square minus 3d plus 2, that is can be written as 1 by d minus 2 d minus 1 x cube, that is equal to 1 by 2. This can be written as 2 into 1 minus d by 2, and this can be written as 1 minus d. Okay, this is unaltered x cube. That is equal to half, and this half is here. Then 1 minus d to the power minus 1. So this can be written here, and this term, this second term is here. The first term is 1 minus d by 2 to the power minus 1, then x. That is equal to half. You just expand this as it is and expand this like this, and then exclude. And now just compute, just simplify. Simplify this, finally you obtain that 1 by 2, 1 plus 3 by 2 d, 7 by 4 d square plus 15 by 8 d 3, and all other term. But in this case here, d4 of x cube is equal to 0. So d4 and higher terms are neglected. So that is half x cube plus 3 by 2, 3x square plus 7 by 4 into 3 into 2x. Just operate this d over d's on x cube. So that will give you this result, and finally y2 is equal to half x cube plus 9 by 2 x square plus 21x plus 45 by 4. So this is the particular integral, and the complete solution is written here. See, this example actually followed the rule, or the rule that is here. This is here. This is actually example of this property is uh, shown or shown in this equation, in this example number 8. Example number 8. So 9, another one is here, 9. So solve the differential equation d square plus k dy is equal to x. And this is another example of the last property. That is here the auxiliary equation is, the auxiliary equation of this will be m square plus km is equal to 0, or from here m has two values, and one is 0 and another is minus k. So the complementary function is a e to the power 0 plus b to the power minus kx. That means a plus e to the power minus kx. Now we have the particular integral. The particular integral is 1 by d square plus kd into x, that is equal to 1 by kd. Okay, you can write this kd as common. So 1 plus d by k into x, that is equal to 1 by k, and this d will give d inverse. Then 1 plus k by d by k to the power minus 1 x. You can write this. So 1 by k d inverse, then 1 minus d by k plus d square by k square and other terms to x. So that is equal to 1 by k d inverse minus 1 by k plus d by k square into x. So just do it. 1 by k is here and d inverse x means integration of x, that is x square by 2. Then minus 1 by k and this x. So that means x by minus x by k. And d of x means 1 by k square. So this is y2. So the complete solution is here. And another one is here. See this problem. This is d2 by dx square minus 2 dy by dx plus y is equal to x e to the power x sine x. This, see, the right hand side has three terms, x e to the power x and sine x. So it is a different kind of problem. And to solve this, you have obtained that two values of m are m is equal to m1 is equal to 1, m2 is equal to 2, so both are equal. So in that case, complementary function is y is equal to a plus bx e to the power x. And particular integral is 1 by d square minus 2d plus 1 x e to the power x sine x. That is equal to 1 by, you can write this as d minus 1 whole square x e to the power x sine x. It is equal to e to the power, and I know that in that case, if this the c e to the power x and c x sine x is equal to ux. So e to the power, it has the form e to the power x ux, where a is equal to 1. So this d should be replaced by d plus 1. So that is equal to, and this e to the power x should be written in the left. So e to the power x 1 by d plus 1 minus 1 whole square x sine x, or y2 is equal to e to the power x, and from here you can understand that 1 by d square will be left there x sine x, and 1 by d square sine x means d to the power minus 2 sine x. That means d inverse means integration, so this is equal to d inverse into d inverse. So d inverse is there, another d inverse is integration x sine x dx. So we have to now use the method of integration by parts. That is done here. D inverse is here, and from here x, then integration of sine x means cos x, plus into minus integration, this differentiation of this x is 1, and integration of these means minus cos x, or plus is here, cos x dx, then dx is here. Okay, no problem. Dx, d inverse of all these things. So that is equal to d inverse. So now d inverse means integration. This is minus x cos x plus, from here, integration of cos x is sin x dx. Now again this first term, you use method of integration by parts, and this term will use sin x, that will give you cos x. So finally we get y2 is equal to minus minus e to the power x sin x minus 2 cos x. So this is the particular integral. So the complete solution is this particular integral plus the complementary function. So y is equal to a plus bx e to the power x minus e to the power x sin x minus 2 cos x. So this is the third part, and this is the end of differential equations, and through some classes we come to know how to solve different kind of differential equations. It may be first order linear equation, it may be second order linear equation, and linear equation, you know that it may be, there are two types, one is homogeneous and one is non-homogeneous. So no problem, any kind of equation can be solved, and we actually learn the everything to solve differential equations. So one thing you have to do, that you just just practice all the calculations, just practice and practice, then everything will be very easier to you.